Makie.jl. So far we have listened a lot about structured data, so we can do scatter plots, heat maps, and stuff like that. But our domain is where we have unstructured meshes and most likely nonlinear fields, and also probably nonlinear geometry. And this is what we would like to visualize with Makie. And what you can see here is two typical examples. On the right is a computation done by Dennis. It's the left heart chamber. Okay, the left heart chamber. Computed with large deformations, so nonlinear relation, and activated. It's an active material which is simulated, done by some chemical process. And on the left is a typical example for engineers and mathematicians who do work in large deformations where you just twist a cube heavily. And so let me start why we do this. So we have this small package which is called ferrite, and this builds on top of Makie and uses then things that are defined in ferrite, which is a small finite element toolbox, initiated by Christopher Carlson and then mainly developed by him and Patrick Hector, and now also by us and many others. And we started it because we needed some visualization tool for teaching. And so you see that the tasks we are facing are not so trivial to solve. So really scaling those plots up with lots of elements. And additionally, it was Corona. So I had to set it up remotely, such that a server holds basically all plots and then distributed through the notebooks to the students, more or less. And this was the first time when I was actively talking with Simon, because back then I did a raw prototype of what is now ferrite, and then we set up JServe with WGL Makie and Web.jl Makie, and in a way that all Pluto notebooks are on a server and the plots are rendered locally. They are not rendered locally, but they are just showed locally on the students' browsers, and they just have to connect to the server by typing some IP in the browser. Okay, so this was the initial motivation. But nowadays, I would also like to use the package in research context. So I want to get rid of ParaView because most of the time it just annoys me that I have to switch my stuff from Julia data into a text-based format, and then maybe I forgot to export something to the text-based format, and then I have to rerun everything again, and the simulations are expensive, so it's a little bit annoying. So what I want to have is an integrated flow in Julia, that I have my computations in Julia, and whenever I lag something to compute while the simulation is running, I just want to recompute it by the data I have in Julia and not re-export something and just visualize it. Okay, so first one, what we wanted to have is an integration between this process. So I want to compute in Julia something that I want to visualize. And if there is a change to this field or this variable, I want to do it in Julia and then directly display it as a visualization. This is one of the main goals for us. And of course, it's nice to have vector graphics output for publication. So fancy color mechanics, as some call it, of course, often part of a paper. And we need very fast visualization for time-dependent problems because there are users which have a lot of elements. So a lot of degrees of freedom, a lot of triangles that we have to render, and we will cover that later. We want something which is easy to extend, of course, because there are a lot of things that are very specific to our domain and are not anyhow related to Makie or something similar. So we would like to provide this in the end. And of course, a backend for the notebook environment, which is of course already there with Web.jl Makie, and which works, at least for us, pretty good so far. So we are still using it for teaching. So we started back then in 2020, and we are still using it. Yeah, and support for nonlinear fields and geometry. And this is more or less the most challenging task, I would say, which we covered partially or solved partially in the package. And so some things work very nicely, some things don't work nicely yet. But yeah, let's see. And the long-term goal, of course, is to have a common interface for any PDE discretization, which is not bound to Ferrite, so this one small finite element toolbox in Julia, but rather to have some package that defines an interface such as with IP or it's there. Yes. So they are pretty exactly pretty guys. So there are many people who solve PDEs and who would like to visualize them maybe in Julia. So this is the motivation for the interface. And so we started, and in the initial version, I just wrote a couple of recipes such that they work out nicely. And you get an idea of what we would like to have is something as shown on this slide. So here you can see how discretization looks like. So we have a custom wireframe because things are a little bit different for us than in the Geometry Basics. Then we have this mesh primitive that we use in the end from Makie to visualize plots. And of course, we want to combine them, and we would like to have deformation by scalar solution. So the primitive is a surface plot, basically. Then the first challenge was to have element-wise constant data so that it's not interpolated in between. I think there was support added then at some point, but we cover it in a different way. And arrow plots if you have a vector field. So this is typical in fluid mechanics that they show some field by arrows. In mechanics, it's more that you deform directly your domain and then you see the deformed body, and that's fine.
So in the first you had for also for the data, or Makie can update zero, well, look so we have zero and that's all the data. On the bottom, usually our physical problem has some kind of tendency. For example, if it's clean and we load it over time on front end, form, so this one here, simply time steps. I mean, it's a very small deformation which we have, so it's a little bit hard to see.
Okay, that's an old delay.
And we also can here look what how we post-process the data. So we give for inputs and how we vector and how we visualize vector. And the ways how we can do it, for example, the components, the norm, or we can compute more stuff from this vector. And we can also, if we would have the fields here, for example, magnetic field, pressure field, or some chemical variables internally, and we could also switch to these. And this is all very easily done with Makie or sliders and up. So what's important here is also that we can also run this while we run the simulation. We can always look at running all no problem involved. And we can also conference here, contact impacts about what are the 4 items. And first, we have some domain with discretized elements, and these elements are positive nonlinear. So the first step is to get from the nonlinear grid triangular representation with the present. However, we are not done just because it's geometry. It's also possible that we have a loosely field on our geometry, which has a different kind of nonlinearity, which would mean a different tessellation. So basically, we have the two-pass algorithm, where we first tessellate geometry, second, we tessellate again the field. And the best thing here is that we can that we have our kernels, also tessellation, for example, or transferring the solution fields onto the discretization. These can act element-wise. You see here some of the details. If we, for example, have a bilinear ansatz or quadrilateral, we have linear in one direction, linear in the other direction, and also non-linear on the diagonal. Then in PDE, we would say that we can discretize a quadrilateral in two triangles in making it. However, this is often done in link framework, but if we do this, then we see here in the center, this is the diagonal mode, it's non-linear. We discretize from 2 to 4 and connect the basis functions onto these triangles. We see that we basically lose this diagonal mode and get the river up. So what we have to do is we have to come up with relations which resolve these mixed modes. And for the reference, which are linear in both directions, it's quite easy. We can just use 4 triangles with the central node or anchor and get a good approximation for our visualization. In the first situation, we just rendered for 3D problems all faces, or also the non-visible internal faces, which was represented as function, so we can get running. The problem of which we often encounter in the final problem is that fields are not always continuous. For example, if you have data variables, molecules continuous, or if you have gradient fields, they are not continuous across elements. So it's usually not the best way to approach the tessellation with conforming triangles on the faces, but we make them non-conforming by splitting on the faces the nodes apart into a number of nodes which are just local on each face. For example, if we have 2 elements, and we split up this and this node here, and into 2 nodes. So we decouple the triangle, but they can also decouple. This has the advantage that if we have some phenomena which we want to view, which are inherently discontinuous, for example, checkerboarding or mechanics, then this allows us to properly see this one. So it's hard to see on the beamer, but you really see that there is some checkerboarding pattern on the domain. And you see it more clearly in this region. But the usual representation, which is a projection, the discontinuous field and the continuous field, which means I'm searching a continuous function, which is closed in some mathematical sense, closest function in some mathematical sense. But here we see that all the checkerboarding is done. So we may lose information about the underlying phenomenon. And also, if we want to visualize gradient field, for example, then you see that on the left, we have linear approximation in the solution field with piecewise and piece approximation in the gradient field, where we have this nice pattern, and you see that things are not really converged in the gradient fields. And for second order approximation, we get a linear, still discontinuous approximation if you look closely for the gradient field. What you see is the approximation there. So another problem with high order is that you need to find a tessellation for it. But to get a really good tessellation, so we don't want to over-tessellate if we have nonlinearity to come with it, almost linear approximations in other species. That's the problem with regular. So this would require an adaptive tessellation, which will come later on. So in our first iteration, we thought, okay, maybe we find a simpler approach, nonlinear fields. And here we have, for example, order free triangle. And we know from the theory that we can find lower order refinement of our field, which still has the important information. And in our frameworks, in the version, we still have our it's in our algorithms. We use the first order refinement. So we search a piecewise linear field for this triangle, and we just choose the nodes of the basis functions to cancellation on our field. And this allows us to get a rough idea about how the higher order fields are related. For example, here we have again the same problem. There's a class Poisson problem. With, here, 2 order 5 triangles as our discretization. And we see here that we get the idea how the solution looks in high order. I think it's not perfect, but it is get it perfect. And another important thing is when we develop this finite element fields, we want to have some information about the actual elements. For example, how are the nodes numbered, the faces numbered, and this just helps us really speeding up the development and see if everything is consistent. We just can look at it and we have already found it.
Yeah, and then the second iteration was just done recently. And then we included clipping. So sometimes when you have a 3D domain, you do not want to look at the outer boundary box, but you rather would like to look inside. And so we implemented this rather simple crinkle clipping algorithm where an element is either displayed or not. And so what I mean by this is all faces of the element are displayed or not. And by this, you get this stair kind of like behavior that you see at the right. And further, we included culling. So it's a basic culling. And culling means that we only render the faces that are on the boundary. This would be the perfect world. But currently we render all faces of all elements that live on the boundary. So it's like a hollow cube in this example, where you have this outer boundary elements and then you render all of them, which are still a little bit more than should be done. But yeah, this is future work to incorporate this then. And further, what I like is that recently there were some improvements in code paths, and I want to stress the last column of this table where we have it's still a rather small example for finite elements, but for Makie, I would say it's already getting quite large because there are 8 million triangles in this example that are rendered. And if we just took our code and Makie 19.2, then we had 70 seconds and a lot of allocations. And then Simon did some really nice optimizations in the code paths. And then all of a sudden it already dropped down to 2 gigabytes of allocations and 15 seconds. And then we further implemented that we use shader abstractions buffer such that the shader abstractions buffer hold all triangles and all the physical coordinates that are just updated. And then we got again some nice speedups from this, but there are still 1.2 gigabytes remaining allocations due to the fact that the shader abstractions buffer is used in the mesh and not a normal mesh. So I have an issue for this, and I would like to work on this at MakieCon, such that we get rid of the 1.2 gigabytes and only are left with, I don't know, whatever is needed. Yeah, then to make things even more weird before we conclude, we also have the case where fields, so physical fields, only live on the part of the domain. So at the left-hand side, you can see, obviously, there's only at the top, the field is living at the top of the domain and not on the whole domain, which is already making things more complicated. Further, you can have mixed grids, so where your discretization is not only consisting of quadrilaterals, but maybe also triangles and I do not know, any kind of elements. You can compose it in any way you want. And at the right-hand side, you see some other field, which is piecewise constant. If you look at the upper triangles and the lower quadrilaterals, and then in between there's a linear interpolation. So this would be just some solution where you have really mixed type of elements. Yeah, so our next steps, So definitely our kernels should work on the GPU because they are really computationally demanding, and yeah, they are element-wise, so should be possible. As Dennis mentioned, we would like to have some adaptive tandem tessellation of the geometric and the algebraic discretization. Then there is a nice concept about superquadrics, where you have basically an ellipsoid, and based on some tensorial data, you deform this ellipsoid, and then you get an idea how a tensorial field is looking in your domain. And for this, we would like to plan to use mesh scatter and then update basically the markers based on some deformation or something in this direction. And isosurface extraction for nonlinear problems. And then in the end, if we have some iteration where we think we discovered all possible combinations, derive a common interface package, which would be then PDE Makie or something like that, which would be interfaced by Trixie with AP, finite tools, or whatever else finite element toolboxes out there in Julia. And then hopefully everyone's life is easier. And yeah, with this, I would like to thank for your attention and then maybe ask some questions.
Comments, questions?
Maybe I ask something. Is there anyone here solving PDEs? Oh, nice. Oh, data-driven or not data-driven? Sorry? Oh, okay. And what kind of visualization? Ah, nice.